All right, good afternoon, cohort A. So this is a really crucial lesson for you. So I'm going to get right to it, okay? And we're going to look at the periodic table shortly. But before we do that, first we're going to look at some what are called physical properties, okay? A physical property is just something that's used to describe an object, okay? It could be its mass, it could be its volume, it could be its color, it could be its texture, its, how well it conducts electricity. It could be a number of things, but you get it's like a description. So I could tell you, like, I'm 6'1". That is a physical property of my body. I have a mass of 80 kilograms. That's another physical property of my body. So I'm made of mostly water. I mean, that'd be another physical property of my body. If you're talking about, let's say, chocolate, a bar of chocolate might be brown in color. It might have a certain melting point. Let's say it melts at 40 degrees Celsius. Well, that is a physical property. So you get it, like, it's basically a description. Now, in chemistry, we say a physical property is a property that's measurable, whose value describes the state of a physical system. So state, the physical system could be an object of some kind, right? And you're just describing it. That's what we mean by physical properties. Now this word extensive, okay, the word extensive means that, like, the property depends on how much of that you have. So say, for example, mass. Like the mass of chocolate depends on how much chocolate you have, right? But its color does not depend on how much chocolate you have. Its color will always be the same, whatever the color of that chocolate is, right? Whether it's white chocolate or dark chocolate or whatever it is. See, so mass depends on how much of the stuff you have. We call those extensive properties. The only two things I can think of that are extensive are mass and volume, right? But then there's intensive physical properties. Intensive properties do not depend on how much of that object that you have, okay? So for example, your hair might have a certain color. It doesn't matter how long your hair is. It's just that color, right? So, like, color does not depend on how much of something you have. Density does not depend on how much you have. How good an electrical conductor does not depend on how much wire you have, right? Like, so copper is a good conductor of electricity regardless of how much copper you have. So you get it, those are called intensive properties. Most properties are intensive. They don't depend on how much you have. Now, a quantitative property can be described using a number. So if I tell you my mass is 80 kilograms, okay, that is a quantitative property. So in other words, you can assign a number to it. If I say the temperature of my core is 38 degrees Celsius, that's a quantitative physical property, right? Now, if I say the color of my hair is kind of rusty-ish, sort of a lot of colors in it, that is not a quantitative physical property. That is a qualitative property, which is not described using numbers, okay? So qualitative properties include color, texture, malleability, ductility. These are qualitative. Boiling points and melting points are quantitative. So if I say water boils at 100 degrees Celsius, that is a quantitative physical property of water, okay? It's also intensive. It doesn't depend on how much water you have. It just boils at 100, right? Whether you have a cup of water or a gallon of water, they'll both boil at 100 degrees, okay? Yeah, so anyway, those are like how we qualify properties. So they can be qualitative or quantitative. They can be described using numbers, that's quantitative, and using just descriptions, okay, like color. If I say, like, oh, that texture of that sandpaper is rough, I didn't assign a number to it. That's a qualitative property, okay? Okay, so here are examples of physical properties. You need to know the definition of all of these things. Some of them are obvious. So color, I'm not going to define that. Color is what color something is, okay? It's pretty simple. Mass is the amount of matter in an object. Volume is how much space that object will occupy. Density is just mass divided by volume, so it's connected. Those three are quantitative, right? Like mass, volume, and density. Texture is like roughness and smoothness, kind of texture. Thermal conductivity, how well does something conduct heat? Okay, like a metal spoon would be a good conductor of heat. and a good conductor of electricity. Whereas a wooden spoon would be a poor conductor of heat and a poor conductor of electricity. Same. Okay. Malleability. This is. I was telling the students today, this can be banged out or hammered. Whoops. I'm having a hard time. Smartboard today. Hammered into sheets. Okay. Like, think of metals. Metals can be hammered out into a variety of different shapes, swords and tin foil and so on. That property is malleability. What I like to compare malleability to is a Rice Krispie square. Okay, Rice Krispie squares are malleable, right? Like you can press down on them and squeeze them out into flat as a pancake, that kind of thing. That's called malleability. Okay. If you like, the opposite of malleability is like brittleness. Okay, when you try, if you, for example, take a piece of glass is not malleable at all. If you try to hammer it out into a sheet, it just breaks, just shatters, right? All right, ductility is the drawn into wires. So you can pull the ability of something to be drawn into the shape of a wire. So again, metals again have a high malleability, high ductility. That's what makes you a metal, okay, if you have those two properties. Melting and boiling points, self-explanatory, so that's no problem. Luster is shininess. So again, metals have a high luster. Non-metals tend to have a low luster. Hardness is just how hard something is. I was telling the students this morning, diamond would be the hardest known substance. Yeah, hardness is a physical property. Metals actually have typically pretty high hardness, not as hard as diamond though. Or glass. Glass actually has pretty high hardness too. Like I can't scratch glass with my metal key. Okay, you'll find it not scratchable with metal. Plexiglass, yes, because plexiglass is softer, so hardness. Elasticity is the ability to reform a shape when deformed. So let's say you take an elastic band and you stretch it. Well, if you sort of release it, it'll go back to its original shape. That property is called elasticity. Brittleness is, like I mentioned, when glass, like it's breakable, it breaks easily, okay, when, let's say, it experiences an impact force. Solubility is, it dissolves in water, let's say, as an example. It's how well something dissolves in water. So, like, for example, salt would have a high solubility. It dissolves easily in water. You mix in the crystals, and then you stir it, and they dissolve. So that property is called solubility. Temperature is self-explanatory. So if I say the table right now is 20 degrees Celsius, it's the temperature of its molecules. That's a quantitative physical property. All right, so there's a list of various physical properties that you'll need to know. I've written out the definition of ones I think are a little unusual, and that's it. All right, so periodic table. We're going to talk a lot about the periodic table today. But we'll, in fact, chemistry, this is your, these are all the known types of atoms, right, are listed here on the periodic table. And there is an organization to it that I wanted to point out to you. First of all, the rows. So there are 7 rows in the periodic table. Here you can see them here, numbered from 1 through 7 at the bottom. The rows are called periods. So I'm just going to write that down here. The rows are called periods on the periodic table. Okay. So you'll hear me refer to the periods on the table. Each row is a period, and there are 7 periods in total. Okay. And there is a list of groups up here at the top. These things are called groups, and you can see on this periodic table the groups are colored. Okay, so Lithium, here I'll circle them, lithium, sodium, potassium, rubidium, cesium, and francium, we call them group 1 elements, or sometimes they're referred to as alkali metals. And so you can see this first column on the periodic table are alkali metals, with the exception of hydrogen. Hydrogen would be in a group all by itself. Normally we consider it a nonmetal, so it's colored green, but it's reactive, so it's a reactive nonmetal. So that's in this category over here of nonmetals. All right, yeah, but hydrogen is very unique, I should point out. It's kind of almost in a group by itself. All right, after the alkali metals in column number 1, column number 2 are alkaline earth metals. They would include beryllium, magnesium, calcium, strontium, barium, and radium at the bottom. Okay, so those are the alkaline earth metals. You'll recognize calcium as the one that's in your bones, whatever, gives you structural strength. Well, strontium has very similar properties, and those would be in seashells, right, would contain strontium, and that give it like structural integrity, just like calcium gives that to your bones. So if you're in the same family, like if you're in alkali metals, you have very similar physical and chemical properties. Same with the alkaline earth metals. So going down that list, starting with beryllium and ending with radium, they have similar chemical and physical properties. Okay. Now, at the very bottom, we have the lanthanoids and actinoids. Okay, that they're part of row 6 and 7. Like they actually don't fit well, and so they separate them out. They would normally fit in here, in this area here. Okay, row 6 and 7. So there's still parts of period number 6 and period number 7. So sometimes we call them rare earths. You don't really need to know much about that. The transition metals are all the pink ones that you see moving across the center span. So like it starts with scandium here, and then all the way over to mercury on the other side, and up to and including hassium here, down here, element number 108. And of course some of the elements 89 through 100 at the bottom are also part of that list. Okay. All right. Moving on, the blue ones here, aluminum, gallium, and so on, indium, strontium, okay, thallium, bismuth, polonium. These are all called post-transition metals. Okay, now I'm going to erase that. They're colored blue. Okay, and we call them post-transition metals. Now, everything so far has been a metal of some kind, the entire table. But once you get to what's called the staircase, I'm going to shade in the staircase for you. I'm going to see if I can use a highlighter to do that. So here we call them staircase elements. Okay, so what I've just shaded in for you there are the metalloids on the periodic table. So metalloids are between the metals and the nonmetals. So they have properties similar to metals, and they have some properties similar to nonmetals. Those are called metalloids. Okay, and I've just highlighted them now for you. Sometimes I call them the staircase elements because they kind of make a little staircase. Everything to the left of the staircase, including the two things at the bottom, the very bottom, the lanthanoids and actinoids, they're all metals. Okay, everything to the right is a non-metal. So starting with carbon, okay, and going all the way across here, these guys, these guys, these guys, okay, those are all reactive nonmetals. Hydrogen would be, I guess, on this periodic table anyway, included in that list. And then finally, the last column, these are all nonmetals too. The last column are noble gases. Helium, neon, argon, krypton, xenon, and radon. These are all the noble gases on the periodic table. Okay. So there you go. There are groups on the periodic table, and the groups are listed nicely for you on this periodic table, where it says a little key at the top. Okay, a little color key. You have to memorize where these groups are on the periodic table, because on a test I'll give you a blank one that doesn't have any colors on it, and I might ask you to either color it in or to name like which elements are in which group, that kind of thing. You'll have a periodic table when you do that, but you have to know where the groups are. Okay, so that's something we ask you to memorize in grade 9. All right, that's it for the periodic table. Now let's get to the really important stuff here. And I went through this with the other class, so now I'm going to go through it with you. Moving right along. Okay, so here's the deal. We're going to look now at probably the most important lesson in the entire chemistry unit, which is like the structure of atoms. Okay? But before we get into the modern model of the atom, we're going to take a look at a little bit of the history. Now, unlike space, where the history I feel is like significant when you're studying space, in this case, the history, like the ancient Greeks did not know much about this, but they did come up with the word atom. So let's talk about that. Yeah, Democritus was a Greek philosopher who lived 400 years before Christ. Okay, and he hypothesized that all matter is made up of indivisible particles. I'm just reading it, called atoms. Now, that's where the word atom comes from. So this word, atom, what he thought was, like, let's say you were to take like a piece of paper and tear it in half, and then take one of those sheets that you tore in half and tear that one in half again, and you sort of keep tearing it in half until you reach a point where you've got a small little bit of paper, whatever it is, a small little indivisible bit of that substance, okay, and that would be an atom of paper, let's say. We later would come to call these things molecules, okay, but molecule means a little lump, but atoms and molecules in the modern context mean two different things. So a molecule does exist. There are molecules and there are atoms, and we're going to learn about those things today, okay, what a molecule is and what an atom is. Anyway, that was around 2,500 years ago, 2,400 years ago or so. So we're talking about a really long time ago. Fast forward about 2,200 years, okay, to 1807, and you got this guy named Dalton. And Dalton built on this model, okay, sort of resurrected the theory of Democritus. He just said, look, yes, all matter is made up of atoms. So this point, this is what Dalton is making. He's saying, let's go with the name atom, okay? And an atom is the smallest bit of something. Now, all atoms of the same element would be identical, okay? So in other words, if you have gold, an atom of gold, if I have one atom of gold and you have another atom of gold, our two atoms would be like identical twins. You could not tell them apart. They're exactly identical in every single way. Same mass, all the same physical and chemical properties. So it'd be an identical particle, okay? Now, atoms of different elements would be different from each other. So if you had gold and I had silver, a silver and a gold atom would be very different, okay? Or at least would be different on some of its physical and, of course, chemical properties. And so it would be a different particle with a different identity, okay? So that all of these things are true, by the way. He's not wrong about any of this. So back 1807, he got something right. He wasn't completely right, but he did get several things right. So these are the things he had right. Now, here's the important one, letter D. Atoms rearrange themselves and form different compounds in chemical reactions. But atoms themselves are never created or destroyed in these reactions. Now, he's right about that too. And that was probably his greatest sort of stroke of genius. So what he's saying is you can make water if you have hydrogen gas and oxygen gas. They can combine to form water, okay? And what happens is one unit of oxygen will combine with 2 units of hydrogen to produce the molecule we're familiar with, H2O. So here you can see what the atoms look like. They kind of look like billiard balls, just like how Democritus might have described them. But the deal is, he got they do react, okay? They do react. Now, he couldn't really explain why they would do this. In other words, like for Dalton, he didn't have a good explanation. That's part of the problem, okay? But there is a problem with his theory. The theory does not explain electricity very well. So how do you explain what's happening when you get a static charge build up? Let's say you take off a sweater or something and you notice static cling. Well, we know that there's such a thing as electric charge. Well, how do you explain electric charge using Dalton's theory? And you really couldn't. And so we need our theory to explain the known phenomenon, okay? And so electricity is a known phenomenon. We need our theory to explain it. Like, why are metals good conductors of heat and electricity? Well, Dalton's theory could not tell you why. Like, it doesn't explain it. And so we need something better. He doesn't even mention charge at all here. So along comes about 100 years later, maybe 90 years later, in fact, along comes this guy. Now the technology has moved along in the 1800s, right? They discovered a way of making current electricity, and so you could do experiments in current electricity. So along comes this guy named Thomson, J.J. Thomson, and what he did was he conducted this experiment where you would heat up this metal here to a high temperature, and it would release particles that were known to be negative. The reason why they're known to be negative is he attached a battery to this positive plate here, so it's positively charged, and there's a negatively charged plate down here. And then what happened was the particles, whatever they were attracted to the positively charged plate. Now, opposites attract in electricity. So therefore, the only conclusion he could make was he discovered a negative charge that was inside all the atoms that were in this hot metal that he was heating up. So in other words, the atom seemed to have a finer structure than just a billiard ball. It seems to contain positive and negative charge, okay? And the negative ones could be liberated by heating it up, okay? So how did he explain this? Well, he came up with his atomic model, and I like referring it to the blueberry muffin, okay? Or if you don't like blueberries, chocolate chip muffin. Okay, they called it a plum pudding model at the time, but that's a bit of a weird reference for us today. So let's go with the blueberry muffin. So this is an atom, according to Thomson. The blueberries are electrons. So electrons are those negative charges that he discovered, now called electrons, okay? Now they're like blueberries stuck in a positive batter, okay? Because Thomson knew that atoms tend to be neutral, not charged, right? So that means like the negative charges had to be balanced by a positive charge somewhere. Now he's right that atoms do contain negative and positive charges. That's true, okay? But here's how he laid it out. He thought of them as like little muffins, okay, where the batter of the muffin is this positively charged sort of blob, and the electrons are stuck in it, okay, attracted to the positive charge of the batter, okay, and that's it. So that was an atom according to him. Now this helped explain electricity because after all, if you heat this up, maybe those blueberries can shoot out of there and you end up getting like a flow of charge, and maybe that explains how electricity works, right? Okay, so now, here's the deal. The story doesn't end there. Along comes this guy. So now this is what date was this? This was 1897. So 10 years later, roughly, 12 years later to be precise. So these guys are now contemporaries, right? Working in the same lifespan, at the same time. 1909, this guy named Ernst Rutherford comes along, okay? And Rutherford, he decides, look, I'm going to test Thomson's model. So he devised a test that's a famous experiment in physics called the alpha particle experiment. Now, alpha particles come from radioactive rocks. Okay, in fact, there's an element on the periodic table called americium, and americium would likely be found in your house and the house's smoke detector. Okay. And what that does is that little mineral, like it's an element on the periodic table, but it's a source of alpha particles. Alpha particles, this is the Greek symbol alpha. They're known to be positive, okay? And I said that in the note here, they are known to be positively charged. They are attracted to the negative plate in those experiments, right? So they're known to have a positive charge. And so what he did was he took one of the most malleable, I think it is maybe the most malleable metals on the periodic table, gold, and you can make it like, think of a piece of aluminum foil, how thin it is. You can make gold foil 1,000 times thinner than that. Okay, you can make it incredibly thin. It's a really amazingly malleable substance. So gold, what he did was he took an extremely thin sheet of gold foil, okay, and he fired alpha particles at the gold foil in an experiment like you're seeing right here. Now, most particles, like 99.9%, even more than that probably, 0.99%, you know, go undeflected. In other words, they passed right through the gold foil like it wasn't there. Now, they actually predicted that if atoms are like blueberry muffins, they actually predicted that that's what should happen. They should all go through. But that's not what happened. Most of them went through, but every once in a while, you would get what looked like a hard collision. So this alpha particle will fly in, here's your sheet of gold foil, and it would get deflected in a hard deflection that way, this way, that kind of thing. And there was a conclusion from this, since these are positively charged, okay, is these deflections, what they prove, these rare deflections, they're quite rare. They only happen like 0.1% of the time, or even less than that. I think it's like 1 in every 100,000 alpha particles get deflected like this. But it proves something. It proves that the nucleus of an atom is not neutral, but positively charged. And since most alpha particles miss, okay, the nucleus must be very small. And therefore the atom is mostly empty space. Okay? So here's the deal. You can't have the blueberries in the batter. Okay? If the blueberries are in the batter, then the nucleus of the atom would be neutral. And if it's neutral, the alpha particle will go right through it. Okay? Because charged objects are attracted to neutral objects. And so it'll actually go right through it like it's not even there. Okay? But the fact that some get deflected proved that the nucleus can only be positive because that's the only way you can repel the alpha particle. And that's what atoms do, is they repel the alpha particle in the rare circumstances where that little alpha particle is on a collision course to the nucleus. Okay? So, I explained that in the paragraph here, but to sum it up, if Thomson was right, okay, if the Thomson model was right, the alpha particles should all go through and you never get any deflections. But this doesn't happen. Okay? What happens is what's on the left here. And this deflection proves that because this is a positive charge that's being deflected, it proves that the nucleus repels the, so this is the nucleus, it proves that it repels the positive charge, which proves that it's positive, okay? All right, so 99% of the mass of the atom is in that nucleus, and the positive charge of the atom is in the nucleus. Now, what happened to the blueberries? Well, the blueberries are now floating around the outside. Let's call them what they are, these electrons. They're somewhere occupying that space, sort of surrounding that nucleus, and they're bonded to it by electrostatic attraction. Remember, opposites attract. But for reasons that are really, well, difficult for me to explain, and frankly, don't make a lot of sense, they don't ever fall in. They can't do that. Okay, to do it would break a rule, and we can only tell you that there's just some kind of weird rule that they have that they could never fall in. The rule itself doesn't make a lot of sense, but there you go. They just can't fall in. All right. So the point is the electrons are now floating around. Okay, so what we thought was like where the electrons are here are really tiny particles. And they occupy a tiny fraction of the empty space that surrounds the atom. Okay? So, you know, the point is these two models are very different. One of them, the blueberry muffin model, the atom itself was quite large, actually. okay, and was not mostly empty space. But the truth is that no, it's actually mostly empty space, which is why most of the alpha particles just go right through. But every once in a while, you get a hit. And when you hit the nucleus, you'll see that the nucleus must be positively charged. Okay, so continuing the story. Chadwick in 1932, so this is about 20 years later, he discovered the existence of another particle in the nucleus. So it turns out there are particles in the nucleus that we had discovered now. The positive particles turned out to be called protons. Okay. Then they discovered that there were particles of about the same mass that were also located in the nucleus. This is what Chadwick discovered. And they were called, because they were neutral, they didn't have a positive or negative charge, they called them neutrons. So what's in the nucleus of atoms? Protons and neutrons. Okay? Positive and neutral objects in the nucleus of an atom. All right, now somebody else came along, Niels Bohr, and from studies, like if you, like it's not going to make a lot of sense, but I'll just say it, okay? Look, the way atoms absorb and emit light is really strange. So let's say you have a coal in a fire. Well, when the coal gets hot enough, it starts to glow. And it'll glow red and then white, you know, like, and that's how it works. We looked at that a little bit when we looked at photospheres on stars. But the thing is that the way atoms emit light cannot be explained very well unless the electrons aren't just sitting around the atom or orbiting around in just sort of some kind of random way, but there's a fine structure to those orbits, okay, where there's very distinct levels, energy levels associated with each orbital layer, okay? And, you know, you'd have to take, you know, I took an entire course in university on the structure of the hydrogen atom, and that's the simplest atom on the periodic table. So the story gets complicated a little bit, but we'll keep it simple for grade 9. Let's just say that there are, like, the electrons exist. They don't orbit. That's not really right. That's kind of a misnomer. But they thought they orbited at one time, so we'll call them orbital shells, or just shells if you like. And electrons seem to fill up these shells according to specific rules about how many can go in each one. Okay? And this is what Bohr discovered in 1913, just a few years after Rutherford did his experiment. Okay, so to sum everything up, we know that there are protons which have positive charge. There are neutrons which are neutral, and there are electrons which are negative. All three of these things make up atoms, okay, as we know them. And let's give an example here. So this little atom here, this would be sodium, actually, okay? And the nucleus, I'll circle the nucleus in red color. Here's the nucleus. This is not to scale. I mean, if it were to scale, the nucleus would be like a little tiny dot right there, okay? And the electrons would not be visible, period. They'd be around, but they're even smaller in size than the nucleus. They're really incredibly small, have almost no mass. But they'd be occupying these orbitals, which are really incredibly far away from that relative to scale, when you think of how big the nucleus really is. But we draw it big because it's easier to draw, okay, quite frankly. Anyway, what's in the nucleus? Well, protons and neutrons in the nucleus, okay? So the nucleus is where the nucleons live. And that's actually a word, the nucleons, okay? And nucleons are protons and neutrons. Okay, so here we have neutrons and protons. And that's what's in the nucleus. Those are the nucleons that live in the nucleus. Now, the electrons do not exist in the nucleus. In fact, they don't go there. They will not go there no matter what. But they are in these orbital shells, okay? And you see I've called them shells here. And here we see an example of 3 orbital shells. Okay, the outermost shell has a name. We call it the valence shell. It's actually a really important word and a really important thing in chemistry. So there's a valence shell, and the valence shell is the outermost shell that surrounds the atom here. So there's 3 shells. There's the first orbital shell, okay, that has 2 electrons in it. The second one has 8, and then the third one just has 1 in this case. And that's it. Okay, so this is the modern atom. There's a little bit of a finer structure to it than what we're telling you about the shells, but we'll discuss more of that later. Let's just keep it simple for now. All right, so now let's look at how to draw Rutherford bohr diagrams and how we understand all the groups and everything else. So we'll keep it, like I said, keep it simple for today, and then we'll move up from there. Okay, number one, if you look at a card on the periodic table. So what I'm going to do is I'm going to zoom in on this table. Okay, so look at these cards. Look at hydrogen, for example. Okay, I want to point out something. Hydrogen is element number 1. The atomic number that's at the top, okay, like so these atoms, each element on the periodic table represents an atom. Every atom has what's called an atomic number. So the periodic table is organized by atomic number. So what does the atomic number mean? Well, that means how many protons you have. So hydrogen has 1 proton in the nucleus. Okay? This number here, the atomic mass, is the number of protons plus the number of neutrons. Now you'll notice that this particular hydrogen atom, since a proton and a neutron would give it an atomic mass of 2, this particular hydrogen atom only has an atomic mass of 1. So if you round it, I know there's a decimal that I'll explain later. It has to do with the way they average out the mass. But, okay, some versions of hydrogen have neutrons in the nucleus. Okay? We call them isotopes. So in other words, if you're hydrogen, you must have only 1 proton in your nucleus. But what if you have a neutron too? Well, you're going to be a little heavier because you're carrying this extra mass. Okay, you'd be about twice as heavy, but you'll still only have 1 proton, so you're still hydrogen. But we give that one a special name. We call it deuterium. Duo means 2, so there's 2 things in the nucleus: 1 proton, 1 neutron. If you have 2 neutrons in the nucleus and 1 proton, again you're still hydrogen, but now you're 3 times heavier than the regular hydrogen, just the 1 proton. And because there's 3 things in the nucleus, we give it a special name. We call it tritium. Okay, and so hydrogen, deuterium. This version of hydrogen is it's called protium, with just the 1 proton and 1 electron. Okay, so there's protium, there's deuterium, and there is tritium. Those are all 3 hydrogen. All 3 of those things are hydrogen. The most common one is listed on the periodic table. That's the protium version, the one that only has the 1 proton and 0 neutrons. Okay? So, moving across the first row, you'll find helium. So in the first row, the rows are called periods, like I explained before. So in the first period, there's only 2 elements. Okay? Now, helium has 2 protons. Right? And that's why it's element number 2. But if you look at its atomic mass, that is rounded to the number 4. So in the helium nucleus, there are 2 protons, but there's also 2 neutrons. Okay? So 2 protons plus 2 neutrons adds up to 4 units. Okay? And that's why the atomic mass is 4, because there's, not only is there 2 protons in the helium nucleus, there's also 2 neutrons. So it has a total mass of 4. Get it? Okay, so the periodic table is organized by how many protons you have. Now we start a new row. Okay, we start a new period at element number 3. So lithium has 3 protons. So that's how many protons it has. And this you would round to 7. So there must be 4 neutrons, because 3 plus 4 adds up to 7. See, so that's how you figure out how many neutrons something has. Now if you go down here, let's pick something more difficult. Let's say you have cobalt. Cobalt has 27 protons. Any atom with 27 protons is a cobalt atom. Okay? And that's the definition of cobalt. You have to have 27 protons. Now, its atomic mass, you round that to 59. Okay? So 27, how many neutrons would I have to have? I have 27 protons. How many neutrons would I have to get a total of 58? Well, if I go let's see, would that be 31, right? 31, yeah, I need to go to 59, I'm sorry. I need to go to 59. So it's 32. So there's 32 neutrons. So 27 plus 32, wow, I'm slow on my math today. It's because I have to go to the bathroom. But anyway, 27 plus 32 adds up to 59. And so there you go, there's 32 neutrons in the typical cobalt. Now, you can have an isotope of cobalt that has either fewer neutrons or more neutrons. Okay, it depends. But like this is the most common isotope, which means like, remember, iso means same, tope means type. So if you have 27 protons, you are cobalt, but you can have a different number of neutrons. In fact, one of the more interesting stories of isotopes is carbon. We call carbon here, carbon has 6 protons, okay, as you can see. It also has 6 neutrons. So there's 6 neutrons and 6 protons for a total of 12, the atomic mass of 12, right? Now, there is we call this carbon-12. That's the most common version of carbon. But there is a version of carbon called carbon-14 that has 2 more neutrons than that. It actually has 8 neutrons. Okay, and that's the one that we use for radioactive dating. So like a small portion of all the carbon atoms in our atmosphere and everything else would be carbon-14. And as long as you're alive, you eat carbohydrates and stuff like that, and your body is incorporating and consuming carbon-14 and regular carbon. But when you die, you stop eating. Okay, and we can use the decay rate of the carbon to tell how long your body's been dead. But in order to do that, you need carbon-14, which is an isotope of carbon that has 8 neutrons in it, and it happens to be radioactive. Okay. All right, so that's how you read the periodic table. Now let's talk about how you draw the diagrams. Now before you start drawing them, there is a rule. Now this has to do with the work that Niels Bohr did. Okay. The first orbital shell, and you have to memorize this, but I'll show you a trick. It's really easy to memorize it. The first orbital shell holds only up to 2 electrons. That's actually really important that you understand this. Now, if you ask me why, how come it's 2 and doesn't hold any more, it's not because of empty space or anything like that. It's not because of some force of repulsion. There's a principle at work that we call the Pauli exclusion principle, which is not a topic we usually cover in grade 9. But suffice to say that the ultimate answer to that question is we don't know why exactly. That's just how it is. So in other words, you can only have 2 in that first shell as a rule. But if I tell you the rule, that doesn't really explain it. It's just a rule. Okay? So like, it's not like planets where planets move in elliptical orbits. For Kepler, that was just a rule, right? But for Newton, he understood that very differently because there's a natural law to explain it. Here, we don't really have a natural law to explain it. We have a name, we have a rule that has a name associated with it. But anyway, that's just how it is. There's 2 electrons in the first orbit. Okay. Now the second shell holds up to 8. There's another story to be told with that second shell though, and the third shell and all the other shells. They can be broken down into these smaller orbits that you'll learn about in grade 11 and 12 chemistry. Let's not go there right now. Let's just say, like, for now in grade 9, we'll keep it simple. The story is not going to stop in grade 9. We'll have more to tell you later. So this is not the final model. There's a little more to say, but it's pretty good. We're getting close to the final model. But the second shell holds up to 8 electrons, okay? The third shell also holds up to 8, okay? And then finally, the fourth and fifth shell hold 18 each, okay? 18, I've mistakenly put 32. And in case you're wondering, the 6th and the 7th shell, so 6 and 7, the 4th and the 5th hold 18, 6 and 7 have 32 each. Now you have to memorize this information only up to number 4. So only up to here, up to 4. And I tell students, like, how are you going to remember this? 2, 8, 8, 18. How are you going to remember those numbers? It's not that hard, I guess. But I'm going to give you a cheat sheet. The cheat sheet is called the periodic table of the elements. This tells you the same thing. Now, get this. This is the coolest thing. It's like you're putting it all together. Let me zoom out so you can see the whole thing. All right, how many elements are in the first period, the first row? The answer is, and I'll highlight these, the answer is 2, hydrogen and helium. So you're going to get a periodic table when you're drawing these things every time. So how many electrons go in the first shell? Up to 2. Well, how many elements are there in the first row? 2. That's not a coincidence. All right, the second shell holds 8. Well, guess how many elements are in the second period, in the second row? There is 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons, 8 elements in the second period. The third period, guess how many? 1, 2, 3, 4, 5, 6, 7. Again, 8. It's not a coincidence. Okay? And I think we won't bother counting them. The fourth shell, let's circle it in red. Fourth shell there has 18 elements in there. And so the fourth period has 18 elements. The fourth shell can hold up to 18. The fifth shell can hold up to 18 also. The sixth shell can hold up to 32. Now, if you look down here, these elements down here actually go in here. So if you count the entire row, there's actually 32 elements there. So you see how it works? I'm telling you, you have to memorize 2, 8, 8, 18. But you're going to have the periodic table. You can just count it for yourself. Okay? The number of electrons that go in the first shell is equal to how many elements you have in the first row. Not a coincidence. Okay? That's why we start a new row. It's because we're starting a new shell at element number 3. Okay? And then we start a new shell again at element number 11. All right, so let me zoom in here again. All right, so now that you know these rules for shells, I'm going to circle these in red. You have to know that. 2 go in the first, 8 in the second, 8 in the third, and they fill from the bottom up. They fill from the 2. You put 2 in the first, and then you go to the second, and then third, depending on how many electrons you have in the atom. All right, so let's get to drawing them, and this will be the end of the lesson. So step 1 to draw a Rutherford board diagram is determine using the periodic table. So you're going to use the P table for this, which is the periodic table. Okay, that will tell you how many protons, electrons, and neutrons you have. Now, just a note, the atomic number tells you how many protons you have, but it also tells you how many electrons you have. Because atoms are neutral normally, and that means that the number of protons and number of electrons is the same number. Okay? Now, step 2, or part of step 1 is the number of neutrons. Well, you get that by just subtracting the mass number from the atomic number. So we'll look at an example in a moment, but I showed you that already. Now, step 2, you just draw the whole thing, basically. First, you draw the nucleus. Really, step 2 and step 3 you can combine, because step 2 is really simple. Draw the nucleus with the correct number of protons and neutrons labeled. And then step 3, draw the orbital shells with a dotted line. And you fill the shells up from the bottom until you have placed all the electrons in a shell. Okay, and usually there's a method to this. I like to put them in pairs because they do pair up. Okay, so let's go ahead and do some examples. All right, let's start with lithium. So, I'm going to do lithium for you, and then I have 2 for you to do for homework. Okay? I'm going to let you do fluorine and chlorine, but I'm going to do lithium and sodium. Let's do lithium. All right, here's the card on the periodic table for lithium. So how many protons? Well, there it is right there. That's how many protons, so I'm going to do step 1. Okay? I've got the number of protons equals 3. The number of electrons also equals 3. They're both equal to the atomic number. Okay? Now we're going to round this number to 7. You round it. You must round the number to a whole number. So the number of neutrons is going to be 7 minus 3, 4 neutrons. Okay? So that's step 1 finished. Now step 2, I draw the nucleus. So I'm going to draw the nucleus with a solid circle. I'm going to write, this is where the nucleons live, 3 protons, 4 neutrons in lithium. Okay? And then what I'm going to do is start drawing the orbital shells. So this is step 3. So there's shell number 1. I'm going to use a dotted line to draw the shells. I'm going to need 2 shells for lithium. Now how many go in the first shell? The answer is 2. But lithium has 3 electrons. So now I must go to the next shell and put the remaining electron in the next shell. Okay? So, and I want you to do something for me once you've done this. Tell me how many valence electrons that element has. So lithium has 1 electron in its outer shell. Remember, valence means the outer shell. So there's 1 valence, and I'm going to write from now on, instead of electron, I'm going to write E with a little negative next to it. Okay, 1 valence electron for lithium. Okay, now that's 3 electrons in total, but only 1 is valence. Only 1 is in the outer shell. Now I'm going to do sodium for you. Now, step 1. And you don't have to write the word step 1. I'm just writing it because I'm explaining it to you. So you have 11 protons, therefore 11 electrons in the neutral atom, and this you're going to round to 23. Okay, so the number of neutrons would equal 23 minus 11, which is equal to 12 neutrons. Whoops. 12 neutrons. Now, step 2. Draw the nucleus. Put the protons and neutrons in there. So it's 11 protons, 12 neutrons, okay, in this version of sodium. You draw the first shell. I have to put in 11 electrons in this picture. So the first shell can hold up to 2. Now I have to add another shell. Well, the next shell holds up to 8. Now, I want to point this out. You usually pair the electrons up at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. Now, what I mean by that is I start at 12 o'clock, then these 2 at 3 o'clock, these pairs at 6 o'clock, and this pair is at 9 o'clock on an analog clock. Okay? And they do pair up, and that's why we draw them this way. Please don't just spread out 8 electrons around that valence shell. That's not how it works. Okay, so that's how it is. Now, I'm up to 10 now. I've got 2 in the first, 8 in the second. Now I need to add 1 more shell because I have 11 electrons in total. I'll go up here to 12 o'clock and I'll stick it there. And again, the outer shell has 1 valence electron. Okay, now why am I talking about the valence electrons? Well, remember that sodium and lithium, okay, are both alkali metals. They're both part of the same group, okay? Like here, let me circle them for you here. Let me erase some of this stuff. Okay, there's lithium and there's sodium. They're both alkali metals. Well, they have one thing in common, don't they? And that one thing is that they both have 1 valence electron. And in fact, if you have 1 valence electron, that's what makes you, except for hydrogen, by the way. Hydrogen is kind of an exception. But that's what makes you an alkali metal, if you have 1 valence electron. Okay? Hydrogen's an exception because the first row only has 2 spots in it. The first shell only has 2 spots. But for anything else, if you have 1 extra electron in your outer shell, just 1 guy by itself, you're an alkali metal, and that makes you very reactive, actually. Okay, and I'll explain why later. But you see, the number of valence electrons determines your chemical properties and your physical properties to some degree. Okay, it's what makes metals metals and so on. So it's very important, that valence shell. It's very important for reasons I'll explain in the next lesson. Okay, when you're with me tomorrow. So valence shells, really crucial. If you have 1 valence electron, all of these guys, all the alkali metals have 1 valence electron. And we always start a period with an alkali metal, right? Okay, so I've got a task for you. And this will end the lesson here. The task for you is you go ahead and draw the Rutherford board diagrams for fluorine and chlorine. And what you're going to find for fluorine and chlorine is they also have something in common. Now, they're both halogens. Fluorine is the most toxic nonmetal on the periodic table. Okay, so chlorine is also toxic. So they're part of the same family. We call them halogens. What's so special? What's similar? What do they have that's similar? And you'll see when you draw the diagram what they have that are similar. All right, so that task is for you, and that ends the lesson for today. Please do the homework. There is a lot of homework. I'm not checking it tomorrow, so if you get bogged down and you're stuck or whatever, you'll have some time to make this up. But if you look at what the homework is for today, the homework today is just this one here. Okay, Rutherford board diagrams and theories of the atom. Just that one. Stop there. Okay. So up to lesson 4. So we are on lesson 4 now. Okay. Oh, well, actually lesson 3 also, I guess. There's this homework here. Okay. So don't forget to do that one there. So, sorry, lesson 3 and 4. So up to there, please. A lot of questions. They're not that long. Okay. Each individual one, but there's a lot there. So take your time. Go ahead and do it. If you have any questions, drop me a line. All right, guys. Have a good day. We'll talk to you soon.